What should the dominant energy source of the future be?
Talking about electricity.
Electricity, the general power grid for the United States.
Okay, so right now it's mostly coal and gas. So 67% of our grid is run by coal and gas right now. Then you get about maybe 10%. Maybe I should write that down. So you basically got 2/3 of the grid is coal and gas. This is declining. This is going up. You get about 10% hydro, and it could be off a little bit. 20% is nuclear. Matter of fact, this might be 6%. I have to check my figures.
Mm-hmm.
It's somewhere between 6
I'll check
and
them too.
10%. Yeah. So your renewables, I think, are around 6%. But somewhere in there, it's adding up.
Mm-hmm.
But so basically, these are your 4 predominant ones.
Okay.
So the idea is to get rid of these. We want to get rid of these.
So
if that leaves these 2.
Okay, because they're what we rely on most aside from those.
Yes. And so of the 2, the one that generates more energy is the nuclear.
Okay.
Just by process of elimination. I mean, it's just, the problem with solar and wind is 2 problems. So they're good sources of energy. The problem is they've got 2 problems. One is they're very dilute, and the other is they're intermittent.
Okay, before we go into that,
Yeah.
how about explain why coal and gas have to be crossed out? If we're talking about sustainability.
Couple reasons. Number 1, they're going to run out.
Let me scoot back a little bit.
Okay.
So they can see what you're writing.
Okay. They're going to run out. That's the first thing. Maybe 200 years, maybe 300 years. Who knows?
Okay.
They're going to last a long time. Centuries, but they're going to run out. They're not. It takes millions of years for them to
regenerate.
Yeah, so we don't have millions of years for them to form. The nuclear will last a lot longer.
Mm-hmm.
Okay, especially in the newer types of reactors. Your older reactors are 0.65% efficient, so less than 1%. The newer reactors, the Generation 4, I'm going to call it Gen 4. Gen 4. They're 99.5% efficient. So
wait, the older reactors are 0.65%?
0.65, less than 1%. So 99% of the fuel gets stored as waste. So you're gonna have over 99% waste. Waste, W-S-T-E. Here you're gonna have less than 1% waste. So this is like almost 2 orders of magnitude, almost 100.
Wow.
It's like a lot more efficient.
Yeah. So when you're talking about this with the efficiency, it's like if you start with 100, units of this the resource that you have to use in the reactor, you're gonna get rid of 0.65%, and the rest you're still gonna have that much waste.
Right. You're gonna have it's over 99% waste. Yes.
All right.
You're kind of flipping it almost.
Yeah.
So here you're using up 99.5% of the fuel. Here you're wasting 99.5%. So the numbers kind of flip on you.
Okay.
So these older reactors are called Gen 2.
And is that mostly what we have right now?
Yes. We have 104 plants. I'm getting a little bit messy here. There's 104 plants that are in operation today, and these plants are being decommissioned. In other words, no new plants have been built in a few decades. So these plants need to be decommissioned. They need to be taken off the line.
Mm-hmm.
So,
okay.
They're also called light water reactors. LWR. Light water is just regular old H2O.
Mm-hmm.
Heavy water is water with deuterium in it, which is an isotope of hydrogen. So they're called light water reactors. And the reason why they were using light water reactors was because the Navy was using them. So Admiral Rickover was the guy who, when the Navy realized that they could, because if you have a ship, say a ship with a nuclear warhead on it, and your enemy, say Russia, you need to have that ship in the Arctic Ocean, that submarine. Mm-hmm. And it has the capability to launch a nuclear weapon on Russia.
Yeah.
You don't want to be going from the United States to Russia. It's a long way.
Yeah.
First of all, you reduce your accuracy, and second of all, in the path it could be shot down, maybe intercepted. So you have these subs that are patrolling the Arctic Ocean. The problem with the sub is that they need to come back to port to refuel.
Mm-hmm.
And now Soviet Union knows where the sub is because they can track it. But if the thing is hiding in the Arctic Ocean, deep beneath where the radar can't reach, okay, and has enough fuel, it doesn't come back for 3 years or 4 years. Now they don't know where it is.
Yeah.
So it's a big deterrent for nuclear war. So the way they get around that is by using nuclear fuel.
So they don't have to keep getting
exactly,
more and more
exactly.
and more fuel.
Any kind of space mission that's going to go, say, beyond Jupiter, it needs nuclear fuel because as you go further and further away from the sun, your solar is getting weaker and weaker and weaker.
Mm-hmm.
So any mission that's close by, yeah, we could use solar, but nah. You need plutonium. You need something that's going to last a long time. Matter of fact, the the plutonium fuel's still good.
Yeah.
And that's been out there for over half a century. So, and again, because of this equation, I'm going to write it right here. E equals mc squared. That is Einstein, okay? Nobody's arguing with Einstein. Einstein's right. Energy equals mass times the speed of light squared. So from a little bit of mass, you get
The speed of light times that by the speed of light
squared. This is the fastest speed in the universe squared. So out of a little bit of mass, you're getting what?
A lot of energy.
A lot of energy. So solar doesn't have that. Wind doesn't have that. That's why they're dilute. My orange marker here, but very dilute. Matter of fact, solar is diluted by 93 million miles of space. So
right.
Solar energy comes from this, diluted by 93 million miles of space. And that energy from the sun helps to create the winds. So you're talking about energy that's coming from the sun, that's nuclear. It is nuclear.
Mm-hmm.
This is this. It's the same thing.
Yeah.
Okay?
And
so just by process,
this is diluted of that.
Solar and wind are diluted forms of this.
Yep.
You don't have the wind without energy from the sun. You don't have solar energy without energy from the sun. The sun comes from nuclear. So there's two kinds of nuclear energy. There's fusion. There's fusion. And there's fission. And both do the same thing. Both take mass and turn it into energy. So every second, tons of the sun are being turned into energy. So the mass of the sun is continually decreasing. And that's through fusion.
Mm-hmm.
Now, fusion and fission both use this mass defect. Fission breaks an atom apart. This fuses atoms together. But they both do this. Okay? This we know how to do. We know how to do this.
That's what our reactors do.
This we don't. Yes, this we don't know how to do yet. So, okay, so let's talk about fusion versus fission. People say, well, fusion will be the fuel for the future. Great. When? The clock is ticking. So you can't say, well, don't worry, we'll go with solar and wind and we'll come back with fusion in the future. Can't do that. First of all, they're too dilute, they're too intermittent, and second of all, fusion won't be available.
And why are we running out of time?
Climate change. Climate change. So climate change, CO2 is increasing. CO2 is increasing, the Earth is warming, and we're not going to have time.
And just to recap, which of these sources emit CO2?
Coal and gas.
And these...
Hydro and nuclear, solar and wind, no.
No.
The only way hydro and nuclear emit CO2 is when you construct the plant.
Right.
You have to have heavy machinery. You have to have lots of cement. The cement does generate significant amounts of CO2 in the construction of cement. The production is a high CO2 emission. But once it's built, both of these, once these are built, there's no CO2 involved.
Mm-hmm.
So, and people will say, well, you know, what if a terrorist attacked a nuclear power plant? Okay, what if a terrorist attacked Hoover Dam? It's the same thing.
Yeah, it's a
Are you going to have
large amount of water.
Yeah, I mean, first of all, can a terrorist attack Hoover Dam? I don't know. It's so many feet of concrete. Like, probably not. But if you're going to say that, well, what about a terrorist attacking a nuclear power plant? Well, they could do the same thing to Hoover Dam. Now you have, if Hoover Dam fails, you know how many people will die? I mean, it will be Lots of people would die if Hoover Dam ever broke. I mean, just be crazy. So you can't say, what if a terrorist did this or what if a terrorist did that? That's ridiculous. So.
Okay, so going on to safety, which one would you say that would be the most safe here?
Well, the World Health Organization and the Center for Disease Control and the National Academy of Science, all three of those organizations have said that nuclear is the safest.
Out of all the different
sources. The figures were, if I remember correctly, deaths per terawatt. I'm getting running out of space here. Deaths per terawatt. Deaths per terawatt.
So for every terawatt you generate with this energy, for this many people would die.
Yeah, for coal, I think it was 170,000. I'm going by figures. For solar, it was 440. And for nuclear, which was the lowest, it was 90. And those are actual figures from the centers. The World Health Organization, the Center for Disease Control, and the National Academy of Science. National Academy of Science. National Academy, that's a D. National Academy. So you don't get three better sources than those three. So these are not my figures. Those are the figures, actual figures from those three groups.
Right.
So, but terawatt. So kilo means thousand, mega means million, giga means trillion, tera means trillion. So you have to do it based upon how much energy you're producing, because solar and wind are very small energy producers right now. Most of your energy, 2/3, comes from coal and gas. And when you add in hydro and add in nuclear, look at the figures. This might be 6. Let's call it 6. There's 6%. Let's call this 6. It might be 6. I have to check my figures for the United States. I'm talking the United States now. So 2/3, 73, 93% right there, 93%. So there's your 6% left over for solar and wind, renewables, geothermal, and all that other stuff, burning wood.
Yeah.
So yeah, I would say that's about 6%. Because I know the nuclear is 19 or 20, about a fifth. These are about 2/3. So yeah, so nuclear is about 6%. Now if you go worldwide, hydro goes up and nuclear goes down worldwide, but I'm just talking the United States here.
Okay. Okay, so I got safety, the amount of energy produced.
Well, safety. The thing about safety is that these light water reactors are not as safe as this new Generation 4. This Generation 4 is much safer. Matter of fact, these can melt down. And we had Chernobyl, Fukushima, and 3 Mile Island where you had meltdowns.
Right.
Now, Generation 4 reactors cannot melt down. They are designed. It's impossible to make them melt down. Gen 4 reactors do not melt down because they're designed the way they're designed. They actually tried to make them melt down and they couldn't. So they were actually trying to make the reactor melt down, and it politely refused.
The reactor, are you talking about the integral fast reactor?
Yes. Yes.
So, could you explain why it cannot melt down? In layman's terms, I guess.
So, these are cooled by water, like water reactor.
Mm-hmm.
So they're moderated by water. Water is a great heat absorber. So, water has a very high specific heat. If you ever put a pot of water on the stove, it takes a long time for the water to heat up. Okay? You put the pot on the stove without the water in it, the pot heats up real fast.
Mm-hmm.
But the water absorbs heat. So when you have a reactor, you have this massive amount of energy coming off, and sometimes you want to wick away the heat so it doesn't melt, so the reactor itself doesn't melt down.
Yeah.
So the water is a great absorber. It takes the heat in.
Takes the heat and
But
brings
this
it away.
Gen 4 reactor doesn't use water. It uses liquid sodium. I'll use liquid sodium. I'll use this pink here. Liquid sodium. Sodium. Now, sodium doesn't absorb heat the way water does. It is a good conductor of heat. So instead of storing the heat, it wicks it away fast. So in other words, with the sodium, it's getting rid of the heat, taking it away from the reactor real fast. As opposed with a light water reactor, the water is absorbing the heat, and then the pump pumps the heat away from the reactor.
Right.
With this here, this is dissipating the heat really, really fast. It's not absorbing as much as water does. It's a good conductor of heat.
Okay.
Remember, your metals are good conductors,
Yeah.
right? Remember, you learned metals are good conductors, non-metals are not good conductors.
Yeah.
So the sodium is a very good conductor of heat. So they did 2 tests. One was they tried to make this reactor meltdown. It's called an integral fast reactor, IFR. And what they did was they did 2 tests, loss of flow and LOC. That's loss of flow and loss of coolant. So the first test they did was they let the reactor heat up as much as it could, full steam. And then they turned the pumps off so that the sodium wasn't pumping away from. So what you do is you pump the sodium and you pump the heat away from the reactor. So what they did was they turned the pumps off. The core temperature went up, core temperature goes up, and then it peaked and it died down. Because it's a passive system. Because the sodium, even though it's not being pumped, it's wicking the heat away real fast because it's a good conductor. The second test they did was loss of coolant, where they actually take the sodium away from the core. Let it heat up.
There's no coolant. Or
no coolant. No coolant.
No coolant.
Yes, no coolant. Remember, the coolant is what cools the whole. In the case of a meltdown, you need coolant.
Yeah.
If you have no coolant, the thing melts down. Now you got a problem. So, first of all, was loss of flow. Turn off the pumps. Second, they drained the coolant out of the system. And it still politely refused to melt down. And that's because of the design of the rods that hold the fuel. In the old design, you have these rods where the fuel, there's pellets put in there, and the pellets are in the rods. So if the pellets are heating up, they can actually expand.
Because that's where the reaction is taking place, right? Within the pellets.
The mass is turning into energy. That's a lot of energy coming out, a lot of heat, a lot of energy.
From the pellets.
So now if you don't cool it, the pellets can break the rods, and now you got contamination. But the pellets were designed to, as they expand, they cool. So it's different design to the pellets. But also the rods themselves were designed that way too.
So they don't.
So that as the pellets are expanding, the rod is expanding. So when a rod expands, if you have a hole, okay, if the rod expands, the hole gets bigger. Mm-hmm. Okay, it's a simple law of cooling things. If you cool a pipe, the pipe gets larger, which means the hole gets larger. So as the pellets get larger and the rods get larger, there is no breaching of the fuel into the rods because the rods are getting larger just as the pellet gets larger. This is all designed. Okay, This is designed this way. You have a design flaw. The pellet gets larger, breaks the rod. Problem, how do we do it? Make a rod that gets larger as the pellets get larger. And redesign the fuel so that as the pellets get larger, they cool.
Right.
So the whole system doesn't even need a coolant. The sodium is redundant.
Just back.
It's just layer and layer and layer of backup upon backup upon backup. So what they did was they took these best scientists in the world and they assembled them together. And they said, look, we're going to give you complete freedom. You don't have to work with a light water reactor because Admiral Rickover said, this is our design. And he had so much power over the government that before Rickover died, nobody could work on any other reactor but an LWR. So the scientists weren't even allowed to work on any other design. So all of our 104 power plants are LWRs, which are low efficiency, less than 1% efficient. Now Rickover dies, a new Department of Energy comes in, new DOE president. He says, you know what, scientists? We can work on whatever reactor you want. They're good, like, oh good, finally. Okay, let's find out every single problem with nuclear energy. The meltdown, waste problem, and they say, let's answer every single problem. And they make this reactor at IFR. And it works perfectly for 10 years. Perfectly. Mm-hmm. 2 weeks before Chernobyl, they do LOF and LOC. Passes with flying colors. 2 weeks before Chernobyl happens. Now Chernobyl happens, and bang, the whole world says nuclear is bad, while these scientists have a breakthrough discovery. And it gets buried on page 58, or whatever.
Yeah.
So nuclear has a bad name. Why? Because of the way things worked out. So yes, if you're going to go with something to get rid of coal and gas, if you're going to get rid of these two, you've got 67% of the stuff. You're left with these two, and the one that's going to replace it will be nuclear. It's the only choice you have. Hydro can't do it.
Explain. Why hydro can't do it?
Because you need a massive supply of water that falls down due to gravitational potential energy. and it turns a turbine. We don't have enough rivers in the United States to do hydro. And we do take the remaining rivers, you're not going to have fish, you're not going to have salmon. You're not going to, once you dam a river, you can't have the salmon going upstream past the dam.
They prevent migration.
Yes, so you've caused a lot more problems because rivers are important to the health of a nation. Very important. And when you go disrupting rivers, that's a problem. So nuclear doesn't disrupt any rivers. You might not like it. You might not like the name nuclear. The N word is a very, divisive word. As soon as you say nuclear, people are like, oh, I'm scared. Well, okay. Well, you really shouldn't be scared because it is the safest. But
And it's the safest with the light water reactors, which is the least safe of the reactors.
Yes, exactly. That's a really important point. This is with a really faulty design. Like Nolan, when you buy a car, now I drive a Honda Civic, and my Honda Civic, I believe, is a Gen 11, which means that 10 generations of Civics have come before it. Now, why do I drive a Civic? Because nothing goes wrong with it. Kids love Civics. A, it's cheap. B, nothing ever goes wrong. Thing just lasts and lasts and lasts. You buy an American car, some American cars, might be maybe a Gen 3 car, like a Ford Fusion has the 3rd generation. Okay, that means that only 2 generations went before it. So every generation that goes by, you fix something that was wrong. People complain about something. Okay, well, let's fix it. So that's what made Toyota and Honda such good car companies. Was in the beginning, they were making crap. And people said, oh, we're so cheap, but it's crap. So people said, okay, well, let's go back and fix it. And that's what happened with the Japanese car companies. They started to fix things. And eventually, they were fixing and fixing and fixing. And guess what? They started to make good cars that were cheaper than American cars. And they just took the market away. So now my Honda Civic is an 11th generation car.
Had 11 generations to roll out the...
Same thing with airplane jets. There's fighter jets. There's F-22s, there's F-15s, there's F-35s. So right now the hot jet is the F-22, the Raptor. Well, that's being replaced by the F-35, which is called a Lightning. Okay, so every time you make a jet, it's much more improved. You see?
Yeah.
So when we talk about jets, an F-35 is a Gen 5, an F-22 is a Gen 4. I think an F-14 is probably a Gen 3. Okay, so every generation you're improving it. So the Gen 5, that's hard to detect with radar. It's designed to deflect the radar. It's also designed to, if the thing starts heading towards the ground and the pilot's unconscious, the plane will sense that the pilot is unconscious and veer up. We're talking.
I'll talk to you about it later.
Yeah.
It can wait. It can
Sorry, we
wait.
just had an interruption with a custodian coming in. So the pilot's unconscious. The plane's heading for the ground, and the jet senses that the pilot is unconscious. But the pilot could be trying to maneuver away from somebody and heading toward the ground. So the computer has to make a calculation. Is he unconscious? And then the computer realizes that if the pilot doesn't pull up now, it's too late. So then, right before that point comes, the plane pulls up.
Yeah.
Now, when the plane pulls up, the pilot's unconscious. So the plane gives the pilot a chance to recover. Well, if the pilot doesn't take control of the plane, the computer takes over and flies the plane. And it will do so trying to give the pilot a chance to recover. It might take a minute, it might take 2 minutes. It wants the pilot to take control of the plane. But if it doesn't, it takes control of the plane to prevent from the thing hitting the ground. So did these early airplanes have this? No. So every generation is better than the last. So when you have problems with nuclear energy, Chernobyl, 3 Mile Island, Fukushima, you learn from those experiences. And you make better reactors that don't have those problems. So why would you throw the baby out with the bathwater? You're going to get rid of coal and gas. You're going to get rid of nuclear too and replace with solar wind. It's not going to work. And fusion won't be there. We don't know how to do fusion.
We need something now.
And something with a lot of energy.
Question at hand, is nuclear sustainable economically? Is it cost efficient?
Well, you just brought up what Phil Murphy had. New Jersey had the people who generate electricity. They rely on different fuels, and one of the fuels they rely upon is nuclear. And so there's some nuclear power plants in New Jersey, and right now with the operators of the nuclear power plants, they can switch over to gas and save money, because gas right now is cheaper. So they just had a voting thing, and Governor Murphy just signed a bill that would subsidize nuclear, because right now gas is cheaper. The reason why coal is going down and gas is going up is because coal is more expensive than gas. So gas, right now we're in the middle of a gas glut because of fracking. So there's a lot of gas, we're shipping it to other countries. So because gas is cheaper, it makes sense for the owners of the nuclear power plants to convert them to gas. So once you do that though, now you have increased your CO2 production.
Fernando, please report to the school counseling office. Fernando, please report to the school counseling office. Thank you.
So once you get rid of nuclear, now you're getting rid of carbon-free electricity. Okay? And the problem with that is that New Jersey is one of the leaders in the country for carbon-free electricity. Mm-hmm. So of all the states in the country, New Jersey is one of the leaders in reducing its carbon footprint because of our nuclear power plants. 40%, almost 40% of our energy comes from nuclear power plants. But those power plants are going to convert it over to gas. Now, if that happens, now New Jersey is not going to be a leader anymore. It's going to be one of the worst states in the country for reducing the carbon footprint. So the owners of the nuclear power plants are saying, look, you've got all this money that you're subsidizing solar. You're trying to go with solar and wind, but the solar and wind aren't filling the gap. Nuclear is. So if you get rid of nuclear, now you've completely flipped the situation, and now New Jersey is no longer a leader in carbon-free electricity. So the bill was to subsidize nuclear. I think it was $300 million they're going to kick in over the next few years to subsidize nuclear. To keep these plants, because we talked about in the first half when I had the writing on the board, to keep those light water reactors running, which should have been shut down years ago. Because had we gone with Gen 4 plants and built some new reactors, we could have shut down those inefficient plants. But those inefficient plants have done a wonderful job. Even at 0.65% interest, they were doing a wonderful job. But now, if you get rid of them, now you're going to have to generate more gas. You're going to have to have more gas now to fill the bill. And now you've just completely flipped New Jersey from a leader in reducing the carbon footprint to being one of the worst states for carbon footprints. So that's why Phil Murphy had to do that, because had he not done that, we would have gone from being one of the best states to generate carbon-free electricity to one of the worst. So there's something that just happened now to just illustrate what I've just been trying to show you. That without nuclear, you're not going to do it. You're just going to have more and more carbon emissions without nuclear.
So I get that for the environment, nuclear should be the pick.
Well, it should be your main energy source. Now, should you have other sources of energy, solar and wind and hydro? Yes. But you asked me what was the main source.
Yeah.
Yes. So if you don't go with nuclear as the main source, it's sort of like making a cake without flour. You can have icing, but you can't have any cake. Mm-hmm. How would you like a cake made of icing? No cake, just icing. Would you? So we're going to have a regular piece of cake. It's going to be this big, but there's not going to be no cake. It's going to be icing. Would you like that for dessert? Huh?
No.
Or would you like a little cake with your icing?
A little cake.
Or would you like a little icing with your cake? Because to me, I don't like too much icing. When I get these things where there's a little bit of cake in the middle, and then there's like lots of icing, and I'm like, I'll take my fork and I kind of put the icing over to the side, and I eat the cake part with a little bit of icing. Kind of divvy it up.
Yeah.
So that's the way it should be. The nuclear should be your predominant energy source, and you do come on top with your solar and your wind. Now, where is solar going to work? It's going to work better in a sunny location. So, are you going to put your solar panels in Maine? Oh, the sun's not so hot in Maine. Maybe Florida would work better for solar. Further south, you're going to get more sunshine. Arizona, Texas, places that get a lot of sunshine. Further south, you're going to get a lot more sunshine. How about the mountains of North Carolina? Maybe we put wind up there. So you take advantage of where the resource is there. Okay,
but I've heard people say, oh, well, I heard this statistic that said if we filled the deserts in Arizona and everywhere with solar panels, they'd generate enough electricity for the whole United States to thrive.
So here's the thing. When I teach physics, we always assume that the wires have no resistance. Well, wires do have resistance, okay? And so you're going to take a wire and go from Arizona all the way to New York. So by the time you get to New York City, there's nothing left. It's
You lose it because
you lost your power.
friction's taken away.
Well, there's
from the
just
energy.
transmission losses. So first of all, you're not going to generate enough electricity. I think the figures are for every person in the United States, you need 2 25-meter panels. Okay, 25 meters is not 25 feet. 25 meters is like 2.5 basketball hoops.
Hoops or field courts?
The height of the hoop is 10 feet.
Okay, right.
So the height of the hoop above the floor is 10 feet. Add another 10 feet plus a basketball hoop up. 25 feet this way. No, 25 feet this way. And 25 feet this way. No, I think it's 25 meters. So it's 75 feet. My bad. So it's 25 meters. So for every person in the United States, you need a solar panel. 25 meters by 25 meters. That's like 75 feet by 75 feet. And by the way, you need 2 of them for every person in the United States. So for every person in the United States, you need 2 75-foot by 75-foot panels. Now remember, on the other side of those panels, you're not going to have any trees, you're not going to have any grass, there's probably not going to be any animals around. So 2, so let's do the math, 300 million people times 2 is 600 million panels, 75 feet by 75 feet. Really, 600 million squares of 75 feet by 75 feet. And you have to put them in Arizona, by the way. Good luck with Arizona. 600 million panels. You think there'll be any place for animals or cactus or people or coyotes or cities? I don't think so.
So
yeah.
in excess, it might not be so.
So you have to have large tracts of land where nothing is going to grow. Because remember, all that solar energy is not going to go to the grass or the alfalfa or the wheat or the weeds and the flowers that grow in the cactus, the different flowers and the different animals that live there. Sure, take all of Arizona, put 600 million panels of solar panels and put 75 feet by 70 feet. You solved it. You just covered the whole damn state. If you could do it. I don't think you could.
Yeah, so if you compare that with...
And now you have to transmit that electricity all the way to New York City. By the time you get there, there's nothing there. So good luck. Good luck. I mean, it just doesn't work.
Yeah.
So it makes no sense. These people who do these calculations are like really their math is off by orders of magnitude. It's not even close.
All right, well, okay. All right. Back to nuclear. Economically. Like, could we use, money isn't, we don't have unlimited money. Amounts of money. Can we spend all this money to have these generation
Okay.
reactors?
So I think we were talking about that before. So
Yeah.
here's the problem. Why is gas cheaper? And we were talking about cigarettes. I don't know if that might have got cut off.
Yeah, good
So so back when I was growing up, everybody smoked cigarettes. I mean, I remember collecting bottles and cans and taking them to the store and getting money for a deposit. And we would buy cigarettes for them. Everybody smoked cigarettes. Movie stars, everybody smoked. Politicians smoked. Everybody was smoking. And then somebody found out that smoking was bad for your health. And there was a debate whether smoking was bad for your health. But the overwhelming amount of evidence came in and said, yeah, it's bad for your health. The National Academy came out and said, look, smoking's bad for your health. So there was a national debate over it, and the evidence came in, and they proved that smoking was bad for your health. So what happened was you had these like bean counters who did these tabulations, and they figured out, you know what? You smoke, and maybe 30 years of smoking, by the time you're 55, now you can't work, you got emphysema, we have to pay for the doctors, inhale long oxygen, and they figured out it's actually costing the country medical cost.
Right.
And so they did the calculations, these people did the calculation, they come up with a number. And they say, this is what it's costing the country. Got it? Mm-hmm. That's what happened.
Yeah.
So they said, this is what's costing the country. So what they did was they said, we're going to go to the tobacco companies and we're going to say, see this amount of money? That's what you're costing our government in lost wages and health costs and doctors and so on. And they said, you're going to pay this. And this is actually what happened. So the tobacco companies, Philip Morris, R.J. Reynolds, all of them had to pay that money. And that went into a big pot. And they figured how much in New Jersey, how much in Nevada, blah, blah, blah. And they gave this money to the states to take care of the people. And then the cigarette companies had to put a warning on the pack. Get it?
Yep.
So the tobacco companies couldn't make money hand over fist anymore. They had to pay for the damage they did.
Yeah.
Get it?
Pretty cool.
Okay. Well, the same thing's true with gas. Gas is doing damage to water supplies, fracking. It's also releasing methane, which is more of a greenhouse gas than carbon dioxide is.
Yep.
So what you need to do is get the same bean counters, do their calculations, how much it's going to cost, climate change, and come up with a figure. And say, okay, gas, you're cheap, but this is the damage you're occurring. You got to fix, when you fracked and you damage their water supply, you got to fix it. And then put that debt on the gas company and make them pay it. And now gas won't be so cheap.
Yeah.
So that's the problem, is that yes, gas is cheap, but it doesn't pay for the damage it does. The coal companies don't pay for the mountains they took down. They don't pay for the containment ponds that they have, because when you have coal, you have to wash it. So you have this pond where you wash it, and then this sludge and the dam breaks and it destroys the town.
Yeah.
Well, they don't pay for that. So make them pay for that, and you'll find out that coal and gas aren't as cheap as they seem to be.
Yeah.
So yeah, nuclear is expensive because you've got to build a nuclear power plant. Now, once you build it, now that thing runs for a half a century, maybe a whole century. Okay? Because that's what's happening. And now that initial cost is spread out over years, like when you take out a mortgage on a house and you pay for it so much by time, and then after a while you're making money. Okay? So when you do your calculations, you got to figure out how much is it costing every society, this form of energy that you're using over the long haul, and then do your calculations. So yes, gas is cheap, and yes, nuclear is expensive when you first build it, but yes, all your costs are in the front end, and the back end, nuclear pays off. So it takes an investment.
Yeah.
Whereas gas, not so much. It's easy to burn gas. You don't have quite the cost to take a nuclear power plant and turn it to burning gas. Pretty easy. To build a nuclear power plant, pretty complicated. You need some really smart people to know what to do. Mm-hmm. But nuclear employs people. Those are high-level jobs. These are really smart people doing go to college and take nuclear physics. Yeah, I think I'll be a history teacher, or I think I'll be a nurse or something like that. And I'm not putting them down, but it's a lot easier than being a nuclear physicist. Mm-hmm. So, yep. But we have to take into account all of those things. So.
I think the biggest thing that I took away, I'll reach to that.
Yeah. Sure.
But was that so the generation 2.
Right.
So what we have, that's what we have now.
Right.
And
any new plant that's being built now is a generation 3. Mm-hmm. So any plant that's built now is a generation 3. I think Obama had a couple built in Georgia, and I think it was Savannah. He had a couple Gen 3 plants built. But the one I was talking about was a Gen 4.
Yeah.
Those aren't being built. No.
And so is it a majority generation Gen 3, Gen 2?
Almost all of them are Gen 2, yes.
Okay. So
now think about it. Just think about it, Nolan. You have fighter planes that are Gen 5.
Yeah.
And with nuclear power, we're in Gen 2. Like, it just doesn't compute.
And it doesn't compute because we have 0.65% efficiency. And we're generating 20% of the grid for electricity.
For the United States.
For the United States. If we turn the same amount of uranium that we use to get 20%, instead of being that efficient, we're, what was it,
99.5%.
0.5%.
Yeah, take that decimal away there.
Oh, yeah.
Yeah, so
what are we going to get from that?
That's Gen 4.
If we use Generation 4 reactors.
But the Generation 4 reactor that was built ran perfectly for 10 years and it was shut down. It was shut down for political reasons.
This seems like so incredibly ridiculously awesome that I don't understand why more people don't look into that.
Well, people are afraid of nuclear, and that's the thing that you could spend another interview on why people are afraid of nuclear, even though it's the safest. So it's once you put the word nuclear there, people get afraid. So, and I think in the last time we talked about nuclear weapons and nuclear reactors. Nuclear reactors and nuclear weapons are not the same thing.
Different grades of uranium and
Well, yeah, because the uranium that's put into the uranium that's burned in the nuclear reactor is not suitable for bombs.
yeah.
It's too hot. The weapons grade can actually be handled. Weapons grade uranium and plutonium can be handled by your hands. You can't do that with the fuel that's in a reactor. It's too hot, so you can't touch it. It's too hot.
Mm-hmm.
So they actually tried to take nuclear grade nuclear material and make a bomb out of it, and it was very unsuitable. So if the best scientists in the world can't do it, terrorists can't do it. So you talk about people working in really advanced laboratories that can't make it out of a nuclear bomb out of reactor grade fuel. Then terrorists can't do it either. So, but people sort of merge the two together.
Yeah.
They think of a nuclear power plant and they think of a bomb going off with a mushroom cloud, and it's not the same. They're two different faces of E equals MC squared. One kills people, the other generates electricity.
Yeah.
So people just get confused. What people should be demonstrating against is nuclear weapons. That is what should be because you now have taken this E equals MC squared and now you are using it on people. That's a problem. And we now have the capacity to really devastate our planet with nuclear weapons. I mean, Soviet Union, Russia has them, China has them, Iran has them, Pakistan has them, France has them, England has them. That's 7 right off the top. Israel, that's 7 right there. Israel has them. So all of them nations have nuclear weapons. Now, Iran, North Korea, those are other countries North Korea does have nuclear weapons. They just detonated it. So the cat's out of the bag with nuclear weapons. But nuclear reactors are not. Nuclear reactors are the peaceful use of E equals MC squared. Nuclear weapons are the destructive use of E equals MC squared. EMC squared is not evil or good. It's just an equation. That's all it is. But you can use that technology to make the world better, or you can make it worse. Blow it up.
Yeah, I think when I first had your physics class last year, I don't think I really had the line drawn very well because I was not thinking nuclear was sustainable at all for the environment, and I was like, it just seems so horrible. And then, as we talked about it more and more, just nuclear that doesn't have that same effect anymore. It's like I don't see the danger much at all.
So the integral fast reactors, for those watching, if you want to look it up, integral fast reactor, and I'll write that out. Integral fast reactor. I'll get my head out of the way in a minute. IFR. This is the reactor we're talking about. It's a Generation 4 reactor, and it's 99.5% efficient. So this is the reactor that we're talking about that could have probably solved climate change by itself, because it's what's called, it's a breeder. What it does is it breeds its fuel. So the fuel, the usable fuel is turned into electricity. And anything that's not usable goes into a molten bath. In that molten bath, there's a cathode and an anode. And they separate any usable fuel, put it back into the reactor. So this is all done inside the reaction chamber itself. So it's done remotely.
Yeah.
It's not like somebody goes in there and puts it back in,
You don't have to do anything.
No, it's all done inside. It's done by robots. So basically, the fuel goes back in, and there's more waste that goes back into this molten bath, and it's like rolling dice. You're going to get some waste, and you're going to get some usable fuel. The usable fuel goes back into the reactor, and it's like rolling dice. You don't know what number you're going to get, but it's like every time you roll, you get another roll.
Yeah.
And so instead of being 0.65%, okay, now it's 99.5%.
Yeah.
That's over 100 times the yield.
So one cycle might be pretty inefficient, but once you take the product of that inefficiency and put it back in,
Yes.
each
So
time
what happens is
more and more
now
waste.
your waste has been reduced by 100-fold. And so what's happening by eating up a lot of this waste, the waste that does come out only lasts for a couple hundred years instead of thousands of years. And we know how to deal with that because we got churches that have been around for a millennium.
Yeah.
We got churches that have been as old as 500 or 1,000 years old. So you put the stuff in a casket for 200 years and now you could just, it's background level.
Yep, so it's less radioactive and you're gonna have less of it.
Because you're getting more of the energy of the decay products. You're turning into usable energy. So you don't have to worry about Yucca Mountain. You don't have to worry about storing the stuff at the plant because now you can take all of the waste because these things, the LWRs, are generating waste. So now you take this waste, you put it in here, and you burn it up. So all of this waste becomes fuel. People say, well, nuclear waste is dangerous. Not really. It's actually a fuel for your IFR. And now people say, well, I don't know what the IFR is. Look it up. Look it up. Look up the integral fast reactor. And they're good. And they did the two tests: loss of flow, loss of coolant. And this is all done before Chernobyl. And they worked for 10 years. 10 years. They worked on this, and the scientific group was called Oregon National Labs. And these are the people who designed the particle accelerators for CERN and Fermilab. These are the best scientists in the world. These are the smartest of the smart of the world. They designed a reactor that was 99.5%, almost 100% efficient. That's crazy. That's nuts. The best solar panel you got is maybe 28%. And that's with the most expensive silicon around, which is very hard to mine. Okay?
Yeah.
But remember, when a cloud goes by, that panel's not generating any electricity. When it rains, that panel's not generating electricity. When it snows, when it's nighttime, when it's winter, and the sun's not out much, those panels are doing nothing. When the wind doesn't blow, your wind turbine's not turning. So that's the problem with your green fuels with solar and wind. Number one, they're dilute, and number two, they're intermittent. So when the wind's not blowing and the sun's not shining, you got a problem. You still need electricity. So this thing here runs constantly.
Yeah.
Yeah. So, and all of the waste that everybody's worried about now is fuel for this thing. So this thing not only solves climate change, it also solves the waste problem.
Yep.
Because now that waste becomes more fuel. You can't say we're going to run out of fuel and then complain about the waste. Well, because this is the fuel. It burns that stuff up.
Yeah.
So it's called Piero. I think it's called Piero processing. I think that's what it is. Right on the slant. That means fire processing, because you're melting these heavy elements, uranium and all these elements. You're melting and putting them in a molten bath, and then you extract it and you put it back
the
into
cathode and the anode.
Yes, it's a molten bath.
Yeah.
Yes. So yes, it's called Piero. I think it's called Piero processing. I think that's, or Fiero. Maybe I get my P's and my F's mixed up. But that's what it is. And this was designed by the scientists to be a way of, again, making a reactor that had no problems at all. Every single problem they came up with, they figured a way around it.
Okay.
So it's sort of like fire, the town has a fire department, and they go and educate people, and they tell people, look, fire, and then they go into schools, and they tell the kids, look, fire is dangerous, go on the floor and breathe, and head for a door, and keep the doors shut, and get outside the house, don't try to grab things. And so the kids are trained, and there's fire extinguishers, because fire is deadly. But we can't get rid of fire.
You need fire.
You need fire. You need fire to cook things. You need fire to heat the house up. You need fire to cook the water, to heat the water up. So you have regulations, and you study about ways to control fire, because fire is pretty dangerous. Well, so is nuclear. Mm-hmm. But you handle it properly, and you study it, and you teach people. And people need to understand that this integral fast reactor was the answer. You had the answer for climate change right here. And what happened? It was shut down. After 10 years of working perfectly, it was shut down.
Because people are scared of it.
Because a certain political party, that's part of their political agenda.
Not to have nuclear, because they think
because the other party was for it. So basically, and this is my problem with politics, I really hate both parties equally, but if one party says A, the other party says B. It's based on splitting people up. And it's time for people not to be split up. It's time for people to be enlightened. It's time for people to come together and say, look, we need to do something. Because you're going to run out of oil and gas anyway. So you have a problem. Maybe it's not your grandchildren. Maybe it's not your children. Maybe it's not your great-grandchildren. But down the line, your great-great-great-grandchildren are going to have a real big problem when the oceans rise and the planet starts heating up. And now that you've waited too long.
And that's when it gets real big. We could be seeing effects right now with the natural disasters that are getting more and more severe, and more.
We're not really feeling the brunt of it.
No, definitely not the brunt.
What's happening, because heat travels to cold locations, so the equator's already hot. So the heat is going to the poles. So the poles are getting the brunt of the heat. So that's why we could actually have colder winters, because the poles, which should be cold,
bringing the cold down to us.
Yeah, these Gulf streams kind of dip down, and so matter of fact, they're saying, and I'm not an expert on this, but they're saying that Europe, as these poles melt and that cold water starts hitting Europe, it's going to make Europe colder for a while. But that's going to fool people.
Yep.
So yeah, all that ice hits the ocean and starts melting. Yeah, Europe will cool up, but it ain't going to last long.
Yeah.
So yeah, we have a certain window that we have a certain amount of time to do something, and if we don't do something, it's going to be harder for the next generation and the generation after that and the generation after that. And really, like in conclusion, from my perspective, there's only two assets that we have to conquer this problem. Number one asset is young people. Young people. Because young people have got to stop listening to older people and saying, no, we're going to study this ourselves. And that's what happens with these school shootings. The kids said, you know what, we're not waiting for the adults to do it. You haven't done anything. We're going to take things in our own hands. We're going to go down to Washington. We're going to go to the governor in Florida. And we're going to say, you're going to do something. And that's what the kids did down in, what was that, Parkland?
Parkland, yeah.
Parkland School. It's good for you. The kids, during the 70s, the kids went down to Washington and said, look, you're not doing anything about pollution. Love Canal and things like this, and the river catching fire, and finally the government did something, because the kids were going, no, you're going to do something. So number one asset is the young people, and number two is their enthusiasm and the fact that they have things like Facebook and Twitter, and I don't even use these things, so I don't know nothing about them. But you guys have the ability to communicate with each other and spread this thing and spread it around. You guys have that ability. So don't wait for the old people to do anything. They're not going to do a damn thing. Seriously. It's the business as usual.
Okay.
I'm going to get a swimming pool and get another car, and I'm good. Get a second home. That's what they're thinking about.
Yeah.
So it's up to you. So the education of young people and their enthusiasm and the fact that they can disseminate knowledge, that's your weapons right there.
I agree.
Okay?
Yeah. All right. I think we did good.
Okay.
All right. Thanks for Cappuccio.
No problem, Mr. Fian.
All right.
Yeah.